All right, stat students, we have randomness, probability, and simulation. So the idea of probability is what we need to understand throughout this chapter. So why do we use random assignment in an experiment? Well, remember when we randomly assign things, it creates two equal groups. Those equal groups, then we can give one treatment, one the other treatment, and since the groups are equal, then we can make a conclusion about cause and effect of the treatments. So, chance behavior is not predictable in the short run and very predictable in the long run. So what that means is the chances that we would get a 1 or a 2 on an 8-sided die is 2 out of 8 because there's 2 possibilities out of 8 total, which is a fourth, which is 0.25. So we could say there's a 25% chance that we roll a 1 or a 2 on an 8-sided die. That's for one roll. But as we roll a few times, we don't know what we're really going to get. After we roll the die a lot of times, then we know we're going to start getting closer to this 0.25 value. And we have an activity in class that's going to help you kind of understand this idea. How do I know that it's 2 out of 8? Well, there's 2, 1 or a 2. There's 2 different things happening out of 8 total. How much should a company charge for an extended warranty for a specific type of cell phone? Suppose that 5% of these phones under warranty will be returned, and the cost to replace the phone is $150. If the company knew which phones would go bad, it would charge $150 for the warranty for those phones and $0 for the rest. However, since the company can't know if an individual phone, in the short run, but knows about 1 in every 20 will be returned, they should charge, well, let's figure this out. If you think about it, again, and we don't know which phones are going to go bad, but if we have a lot of phones, this long run probability, then we can kind of figure things out. Well, if 1 out of every 20 will be returned, that's a 0.05 chance that the phone doesn't work. If it's $150 to replace it and there's only a 0.05% chance it happens, we would just going to multiply this times 150. And that's 750. So they should charge $750 for this insurance because that would be fair. But to make a profit, they're probably going to charge a little more, like $10, which if you get lucky and you have a bad phone, you're going to save a whole lot of money. But if everybody's buying these, then the company's still going to be okay. So myths about randomness. So let's say we were flipping a coin. Which of the following outcomes is more likely? Tails, heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, 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 tails, tails, tails. Well, again, it's a trick question. All of those are equally as likely because each flip of the coin has no memory of the next one. So the probability of getting a tails would be 0.5. The probability of getting a heads would be 0.5. The probability of getting this tails would be 0.5. And it doesn't really matter what you got before. So even though this seems pretty unlikely and this seems pretty unlikely, they all have the same chance of happening because this is just as unlikely. So we're going to talk about simulations. We're going to use simulation. We already have a little bit, and we're going to create them. We can create a chance process that models the given situation and look at possible results. So what is the question of interest? Describe a chance process to imitate one repetition of the process. Describe clearly how you will assign values. Then you will perform many operations of the simulation that get that long run probability going, and then use the results to answer your question. So that's the process that we're going to go through. I've kind of given you the process so far, and now you're going to start making your own. So we have examples. Suppose a basketball player has a probability of 0.75 of making a free throw. Explain how to use each chance device to simulate one free throw by the player. Well, if we have 8-sided die and there's a 75% chance of making it, well, that's like 3/4. Or we could say 6 out of 8. So what we could do is we could say if you roll a 1 through 6, that would be a make. And if you roll a 7 or an 8, that would be a miss. See how that would be one shot if we were to roll the dice every time, and then we would do a lot, and then we would start looking. A random digits table, well, we could do 01 through 75 would count as a make. And then we could do 76 through 99, and 00 for 100 would be miss. Same sort of probability. Or with a random digit table, we could have also used the 3/4 probability. That would make this easier. We could say 1 through 3 would be a make, and 4 would be a miss. If we wanted to use a standard deck of playing cards, I would do the same sort of 3/4 idea. I would pick a suit. I would say a club maybe would be a miss, and then all the other suits, spades and hearts and diamonds, would be make. See how it's all representing the same 75% chance? And one shot would be one flip of a card if we were to shuffle this and pull a card out. One shot would represent one number from our digit table, and we would ignore all the numbers that are not mentioned, like in this one. Here's another example. Suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper and mix up the papers in a large bag. Just as I am about to select the first name, a thoughtful student suggests I should stratify by class. I agree, and we decide it should be 4 seniors and 2 juniors. However, since I have already mixed the names, I don't want to separate them all again. Instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means, however, that I may need to select more than 6 names. What is the probability that I will draw 10 or more names? I don't have a random digits table in front of me to answer this question. Again, I have 60 seniors. I would make 01 through 60 represent seniors, and 61 through 90 would represent juniors. Okay, so we could just look through the random digits table. I'm going to use the random number generator and show you how this is going to work. So I'm going to represent one round. Remember, once I get 4 seniors and 2 juniors, I stop, and I want to know what is the probability that I will draw 10 or more names. So for one trial, I am counting how many times I draw until I get 4 seniors and 2 juniors. So let's do one trial. Remember, menu, probability, random, random integer. We want numbers from 1 to 90. If we were using a random digits table, we would have to ignore 91 through 99 and 00. And let's start drawing. So we have a junior, a senior, a senior, another senior, a junior. So I have my 2 juniors, so if I get any more, I don't count it. And a junior, that doesn't count, so that's 1 extra. And a senior. So now I have my 4 seniors and 2 juniors, and it took me 7 numbers. So it took me 7 draws that first time. Then I would repeat, but now I'm going to take more at a time. So I have 25 senior, 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 and then 2 is a senior, so there are my 4. 66 is a junior, and 88 is a junior. So it took me that many. 1, 2, 3, 4, 5, 6, 7, 8. It took 8 that time. So an 8 would go down. And I could keep repeating this. So what this is below, the results of 50 trials are on the dot plot below. What would you estimate the probability would be? So here's 50 times. We ran it all the way for you. And it took 10 or more, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of those 50 times. So the probability that it would take 10 or more times to draw out the names would be 11 out of 50. So there's our estimate of the probability. Now, as we do more than 50 trials, we'll get closer and closer to what the true probability is. So that section's not so bad. It's going to take you a little bit of time to get used to writing these simulations.